Now we will see some considerations of statistical learning theory. We will only see two or three ideas inside the statistical learning theory, which is the theoretical study of machine learning. It will be quite theoretical, but we will be able to grab some insights from it. It will prove useful, especially to understand some complexities and some pitfalls that we may encounter when we will train some machine learning models. Also, these will prove useful for us to grab fundamental properties of machine learning. So we have seen in the training phase that we learn from the data. But learning from the data doesn't seem a natural way of learning. We don't know a priori on how we learn from the data. Let's say f of xi is the prediction of the model or model output. For the ith example or the ith data point. In order to learn from data, we need the model to know when it performs good and when it performs badly. So that for that we need to define the loss function. The loss function is really a function that will give us a measure on how far the model prediction is from its label. Let's say we provide an input to the model and receive a prediction. The prediction decides how high is the loss. If the prediction is closer to the expected value, the loss is low, else the loss is high. Here we can see the mathematical notation of loss. The idea here is that the prediction f of xi is equal to the label yi. The loss will be equal to 0 because there is no error. An example would be in case of spam filtering. The model predicts a spam as a spam email. If it's different, if for example the model predicts that an email is a spam, but if in reality it's not a spam, then we have a loss equals to 1. So we can see that loss in case of binary classification is a way of measuring the performance of a model. Now let's see the two most frequently used terms in machine learning in the context of model training. These are overfitting and underfitting. To learn what overfitting and underfitting are, we need to understand the decomposition of an error. So in the equation here, we have different types of classifiers represented by an alphabet F. Let's just review them for the moment. Let's say Fn is a train model that we train on some data. Now F-base is a theoretical model, which is the best model that is possible with the current set of features that we have, with the data that we have, with the information that we have. Empirical risk, which is denoted by the alphabet R in the current equation, is just the average loss of the model computed on all the examples of the dataset. Since F-base is the best model, the empirical risk of this best model is minimum possible that can be achieved with the features that we have. We may think that minimum possible risk that we can have is 0, which is true in a case where a model can perfectly classify, but provided that the features are manually created and it is not possible to cover each and every complexity using the features, the ideal minimum possible risk is not 0, but indeed it is a reference point. Let's say that we have another classifier which is f of capital F. F of capital F is also a theoretical model, and it corresponds to the best possible model with the chosen algorithm and the current set of features. Let's say we choose to train a decision tree. Now, the difference between f base and f of capital F is that f base is the best possible model provided the chosen set of features regardless of the algorithm chosen, whereas f of capital F is the best possible model or best possible decision tree that we can train with the current set of features. So in the equation, the left side corresponds to the difference between risk of our model and the minimum possible risk. This can be decomposed into what is shown in the right side of the equation, that is the sum of the estimation error and the approximation error. We can observe that we just included f of capital F in the right hand side of the equation. Once we added and once we subtracted. So the overall, it remains the same. Let's see what an estimation error is. Estimation error is the difference of the risk of our training model and the risk of the best model that we can achieve with the same type of algorithm. So in the decision tree, we can imagine that if we train our model on the training set, the chances of this model being the best possible decision tree, provided the data, is quite slim. There can be many factors possible. One of the factors is the training time. While training a model, it may be possible if the training time is quite high. To achieve a high performance, we have to maintain a balance between the training time and the performance achieved. In case we stop training the model at a certain time, it may be possible that it has not acquired its utmost learning capacity. So the estimation error really corresponds to the gap that our model has with the best possible model, provided the same algorithm. We can see on the right side, of the equation that we also have the approximation error. The approximation error is theoretical because we can see that the formula for approximation error is the difference of the risk of the classifier f of f, which is the best possible classifier provided the set of features and the algorithm, and the risk of f base, which is the best possible classifier provided the set of features regardless of the algorithm. Here the idea of approximation error is the characterization of the algorithm that we chose. Basically, if decision tree, for example, is too restrictive or is too simple, it may not be able to grab the complexity of our data. We may choose decision tree because it's easy to train and interpret, but we suffer a loss in performance because of its simplicity. The approximation error will be big in case where the chosen algorithm, example decision tree in certain cases, is too simple. Another name for estimation error is variance. Approximation error is known by the term bias. There is a famous concept of bias-variance trade-off. Generally, we are not able to find models that have a low bias and also a low variance. So when we choose an algorithm and when we train, we have to find a trade-off between the two because it's very hard to have both the values low. So the time is now that we know what is overfitting and underfitting. So as we understood, the bias corresponds to a large approximation error and a very small estimation error. This phenomena is known as underfitting. The idea here is that when we underfit, it means that our chosen algorithm is too simple and is not able to grab all the complexity of our data. And that's the reason for a large approximation error. It may help in remembering that we can get an idea from the name as well that we approximated too much. In the other case, where we have large estimation error but a small approximation error, corresponds to a situation where the difference between the risk of a chosen model and the best possible model of the same algorithm is quite high, which indicates that the model is learning by heart all the examples provided to it and tends to always find the same examples in a new dataset. This phenomena is known as overfitting. Overfitting means that the model learns all the data kind of too much than required. And by doing so, it is missing the true signal of the data that was meant to be learned. Let's discuss this further with the help of a pictorial representation. So let's take this example. Here in the figure, we have features in the horizontal axis, and in the vertical axis, we have labels. Now, this is a regression scenario because we can see that the label is a continuous variable. Vertical distance from one dot and the corresponding point in the curve corresponds to the error of our model. So in the center, we have an almost ideal function. It seems to be pretty good because on average, the vertical distance between the dot and the curve, or we can say error, is quite small. So we can say that it's a good fit because it's learning almost the true signal, but we can see that it's not perfect, like we still have some error. Now let's take a look on the figure on the left. Here we can observe that the features are negatively correlated to the labels, but the model makes pretty big errors on average because the vertical distance of the dots and the corresponding points on the curve is quite large. And we discussed before, this is what we call underfitting because it represents an oversimplification of the data. It seems that the model could have learned more from the data. Now the case on the right is an overfitting case. Here, the model learns so much from the data that it is overfitting to the data. Although the model is learning the true signal of the data, it is also learning the noise in the data. And it can hurt the performance. Since the error is small, we can think that it's good, but let's have a look of what happened close to the edge. We can see that there's a huge drop to a negative value or to a small values. So probably here we allow the model to be so complex and to have so much freedom in the end that the model wants to fit to the blue dots and it misses the true signal. We talked about the noise here. In real data, we always have some noise. The noise or a type of randomness can come from different sources. It can come from when we observe the features or when we observe the data, etc. Let's say if we take some physical measurement, example, when we measure height of people, then we have some specific precision that is associated with each measurement in meters. Now, noise can also come from natural occurring randomness. Example, if we take the values twice. Also, noise can be there if we fail to identify an unobserved feature that is adding some noise. Just to summarize, underfitting is an oversimplification of the data, and overfitting is fitting to the noise of the data. Now let's try to understand what is training error and holdout error. So in this case, we still have an overfitting and underfitting scenarios. Here is the plot where in the horizontal axis we have the model complexity, and the plot is for each type of complexity. The average error is there on the left hand side in the vertical axis. So we can see here that we have two types of errors: the blue one, that is training error, or the red one, which is holdout error. What we generally do in machine learning is cross validation. In cross validation, what we do is that we take some training examples in the training set that is used to compute the training error represented by the blue curve, and we feed these examples to model to learn from these examples. We keep a separate data set without intersection between the two. So we have no example that is there in both holdout dataset and in the training dataset. The purpose of doing so is called the true error. Now we discuss, as we discussed before, that if the model is very complex, it will remember the specific examples by heart, and we do not want that. To have an idea of what true error is, we give the model some examples that we separated from the training set before the start of training phase, and then we compared the model predicted label with the true label. The objective here is to have an unbiased estimate of the error, that is the true error. The one that we are interested in, because the model was not trained on this example, so it was not able to learn it. So let's continue to analyze the figure again. We can see on the left part that both holdout error and training error are moving in the same direction when we decrease the model complexity. Both are pretty close to each other. Now we discussed this before. In case in the high bias, we have an oversimplification of data. So we have high error between holdout and training. Both errors are evolving the same way in the sense that the model is not complex enough to grasp all the complexities of the data. If we observe the right hand side, we have a lot of complexity, and the model is introduced to some complexities, and it starts to remember all the training examples. Hence, we see a very different error rate between the ones that is computed on the training set and the holdout set. This is really an indication of overfitting. If our training error is very low and our holdout error is very big, it indicates that our model have learned so much from the training data, learned by heart, that it doesn't generalize well with the new data. that it didn't see. To attain a bias variance trade off, what we want to have is a model that is complex enough, but not too complex, kind of in the middle zone. So that's it for the lecture. I sincerely thank you for listening. If you have any questions or concerns, please feel free to reach out. In the second lecture, we will go deeper in machine learning engineering. We will also have an overview of the life cycle of a machine learning project and will give a deeper understanding of the model design phase. So stick around, see you soon, and have a good day ahead.